Jnanam Paramam Dhyayam. Knowledge is supreme.
We have now defined associated prime ideals of a modulo or a commutative ring, and we have proved that when the ring is Noetherian and the module is finitely generated, then the set of associated prime ideals is a finite set. Now, one little observation about the associated prime ideals. This is very useful for computation. So, this theorem says if A is Noetherian and V is finite A module, if S is a multiplicatively closed set in A, multiplicative closed set in A, also we assume in general 1 belongs to S. So, that means S is actually submonoid of the multiplicative monoid of A. Then if I look at the module S inverse V, this is a module over the ring S inverse A, and if I want to know what are the associated prime modules of this module as a module over S inverse A, this is precisely all S inverse P, where P is running through the associated prime ideals of A, prime ideals of V, who do not intersect with S. P intersection S is empty. So, I am going to leave the details of the proof as an exercise. This is very easy because all that we need to check that. So, for example, I want to check that this inclusion I want to check, this inclusion, suppose I want to check this. That means what? I have to take associated prime ideal. So, to check this, so let P belonging to associated prime ideals of V and P do not intersect with S. Then I want to prove that, S inverse P, first of all S inverse P is now a proper ideal of S inverse A, because P does not intersect with S, and this prime ideal S inverse P, this actually is associated prime ideals of S inverse V as a S inverse A module. To check this, I have to produce an element in S inverse V, so that it is an annihilator is precisely S inverse P. Originally that P was associated, therefore P is an annihilator of X for some X in V, X non-zero, and now the candidate we should look for is annihilator of S inverse A as S inverse A module of the element X by 1. I should prove that this is precisely equal to S inverse of P. If you prove that, then we are done. But this is very easy because you have to prove that any element here annihilates this, and conversely any annihilator of X by 1 is contained here. So, to see this, first of all, so take any element here which is of the form A by S, and you multiply this by X by 1. This is Ax by S, but this is 0 by 1, which is 0 in the ring S inverse A. So where this A by S is an element in S inverse P, that means A is in P and S is in S. Therefore, so it proves this inclusion. Conversely, we know that P is a prime ideal. So therefore, if A by S is an element in S inverse A with A by S times x by 1 is 0, this means 0 by 1, then this means, so that means there exists a T in S with, when I cross multiply, so T times Ax is 0, but T is in S, therefore T cannot be in P because P and S don't intersect, and this is 0 is always in P. So therefore, and T is not in P, therefore we conclude that so therefore we conclude that Ax is 0. Therefore, A belong to annihilator of X, which was P, and therefore these belong to, therefore this element A by S belong to S inverse P. So that proves this inclusion. So therefore we have proved the one inclusion in the theorem, and I will leave the other inclusion as an exercise. So the other inclusion, this inclusion, we have left it as an exercise. So it explains when you pass on to the localization what happened to the set of associated prime ideals. So among them, those who intersect with the given multiplicative set, they disappear, they become unit ideal, and the remaining ones are still associated to this. Now we come to support of a module. Support of a module. So support of a module and the set of associated prime ideals of a module are very closely related. They are not exactly same, but they are very closely related. And what is the close relation, that we will find out now. So first of all, let us define definition. So V is an A module, then support of M, support of V. This is by definition all those prime ideals P such that when I localize V at P, this module is non-zero. This is a subset of the spectrum. And note that we have, this is a topological space with Zariski topology. So where we have given or declared what are the closed sets in this. They are precisely the V of some ideals. So anyway, so now this is a closed, this is a subset here in a topological space. So it is natural to ask what kind of a subset is it? Is it open? Is it closed? And so on. We will prove that this is a closed set. And how do we find the, how do we find it? How do we find by using V? That is the task. So, so note that if I take V equal to A, then what is the support of A as a module? This is precisely all those prime ideals, all prime ideals, because when I take any prime ideal in A, and if I localize, this ring is non-zero, because this is, in fact, this is a local ring. AP is a local ring, with unique maximal ideal PAP. This is, and PAP is the maximal ideal, therefore it is not the unit ideal, therefore this is properly contained there, therefore this ring cannot be 0. Note that here when I write this notation A localized at P, this means we are taking the complement of P, because P is a prime ideal, this complement of P is a multiplicatively closed set and 1 belong there. So S inverse of that is precisely this, that is our notation. So therefore, when the module is equal to the ring, then the support of A as a module is the whole spectrum, and therefore it is closed. So in general, that may not be the whole thing, but it will be a closed set. That is what we want to prove it. So in fact, so the theorem we want to prove is the following theorem. So let V be a finite A module we are not assuming A is Noetherian, then support of V is precisely equal to V of annihilator of V. Now this is little bit inconvenient here, but this V is by definition, this is, recall the notation, I will recall. So before we prove this, we should be clear about the notation. So recall that for an ideal A in the ring A, we put V of A. This is by definition all those prime ideals in the ring which contains that given ideal A. This is a subset of the spectrum, and we know the Zariski topology. The closed sets are precisely this collection V of an ideal where A varies in ideal in A. This collection forms a closed sets in a topological space. They satisfy the properties of the closed sets in a topological space that we have seen in earlier lecture, and this topology on the spectrum is called the Zariski topology on spec A. This is what the notation is, and we want to prove that the support of a module is precisely V of the annihilator. All right. So what is it we want to prove? Let us explicitly write it down. So proof. All right. So we want to prove that. So to prove support of M, support of V, this is precisely all those prime ideals in A such that P should contain annihilator of V. This is what we need to prove, because this is precisely V of annihilator of V. This is what we have stated, right? So now I want to prove this. So I will prove this inclusion first. So we are proving this inclusion. That means if I have an element prime ideal in the support, then I should prove that it contains the annihilator. So let P belong to the support of V. So that is what? That means V localized at P is non-zero. And what do I want to prove? I want to prove that, so to prove annihilator of V is contained in P. So suppose not. Then what? That means I can find, if this is not contained here, then I can find an element in the annihilator which is not in P. So then there exists T in the annihilator of V which is not in P. And remember what we want to prove? We want to now get a contradiction. To what? We will get a contradiction to this. Okay, so now let us take any element of V by P, V localized at P, any element x by S. This means x is in V and S is in A minus P. You take arbitrary element, then V by x by S is also same as, I can multiply up and down by that T I have chosen. So T x more divided by Ts. These are same, that is a localization, and but T is in the annihilator. So therefore the numerator is 0, but then this is a 0 element in V localized at P. So x by S, so I have proved that if I take arbitrary element in the localization, then it is 0. So that means we have proved that the module V localized at P is 0. But then that contradicts the fact that it is non-zero. Contradiction. So therefore we have proved this inclusion. Now conversely, so this inclusion, what do we want to prove? We want to prove that, so let P is the prime ideal with P contains annihilator of V. I have given the prime ideal in the right hand side, and to prove P is in the support of V. That means V localized at P should be non-zero. This is what we want to prove. All right. So now, what is the other assumption we have? We have assumption that V is a finite module. So that means V is generated by finitely many elements. So let us say V is generated by AX1, etc., etc., AXR for some elements, R elements x1 to xr in V. This means every element of V is a linear combination of these x1 to xr. That means V is generated by these x1 to xr. That is we have given, and we want to prove now that P is in the support. P contains the annihilator. So what is the annihilator of V? Annihilator of V is the annihilator of this sum A x1 plus 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 A xr, because V is equal to this. And what is the annihilator of the sum? That is the intersection. So intersection I is from 1 to R, annihilators of the elements ideals, the sum module generated by AXI. This is the but this is the intersection of these ideals. So these, let us call, if you call these ideals to be AIs, these are the ideals in the ring, and this is the intersection of that ideals. And if you have intersection of the ideal, that will contain the product of the ideals. So this contains, this is intersection is bigger than the product, A1 to AR. So this is what we know about the annihilator. And now we had given P. So since P is a prime ideal and P contains annihilator of V, which contains the product, and because it is a prime ideal, therefore it will contain one of them. So therefore P contains AI, which is annihilator of AXI for some I from with 1 less equal to I less equal to R. There exists an I, so that this P contains this ideal AI. This is where you have used the fact that P is a prime ideal. But then that means what? That means if I look at if from the ring A, if I go to the ring, the residue class ring A by annihilator of AXI, this is the ring, the residue class ring A by AI. So if I pass on from here to here, P is the prime ideal here and P contains this AI. So therefore P will continue to be the prime ideal, that I will denote by P bar. P bar is P by AI. So this is the prime ideal in the residue class ring. So this P bar is a prime ideal in the ring A by AI. All right, and what is now A mod annihilator of AXI? So why do I write so much? Look at A modulo AI and then the localize at this. Think of this as the A module and localize at P. That is same thing as A mod AI, this ring localizing at the P bar. That means what? That means localization commutes with the residue. So whether I localize first or I go mod and then localize, these two operations are same. But then what is this? This is definitely non-zero. This is definitely non-zero. Because this is non-zero, because this is a prime ideal in the ring, this ring, and it's a so it's non-zero because it's a proper ideal. P is a proper ideal. I have noted that if you take a ring, then every element in the spectrum is a support. So this P bar is in the spectrum of this. So therefore, as a ring, this one, every element of the spectrum of that ring will be in the support. So therefore, what we proved is A modulo the annihilator of AXI. This we know. This localized at P, that is this side. This is this. This is, and this inside module, this is isomorphic to the submodule of V generated by Xi. This we have seen that these two are isomorphic. It's seen in the beginning. So therefore the localization is isomorphic. And therefore we know because this is non-zero, this is non-zero, see this is non-zero, so therefore this is non-zero, this is non-zero, but this is a sub of V localized at P. So this is non-zero. So therefore what we proved is V localized at P as a non-zero submodule. In particular, the module should be non-zero. V localized at P is non-zero, and that is what we wanted to prove. So we have proved that the support is precisely the V of the annihilator of the module V. So in particular, it is a closed set in a Zariski topology. So all right. So now the next theorem is also equally very important, that now gives a connection between the associated prime ideals. So the next theorem is now I will assume let A be Noetherian and V finite A module and we have a chain of submodules of V with the successive residues Vi by Vi minus 1. These are isomorphic to A by Pi, where Pi's are the prime ideals. I is from 1 to n. Okay, then remember we have proved earlier that the associated prime ideals of V, this is contained in P1 to Pn. This we have proved earlier. And now I am saying that this is contained in the support of V. Moreover, associated prime ideals of V, this set and support of V have the same minimal elements. With respect to the natural inclusion. All right. So, proof. We have already proved that the associated prime ideals of V is precisely contained in P1 to Pn. This we have already proved earlier. All right. So, and what do you know how these PIs are? A mod PIs are precisely the ith subquotient. So, this is isomorphic to Vi by Vi minus 1. That is what it is given to us. So, therefore, when I localize, now this is the residue class ring. So, when I localize A mod Pi at Pi, this is definitely non-zero. Same reason, because this is a ring, this is a non-zero ring, because Pi's are the proper ideal, this is non-zero ring, and this is a localization of that ring, therefore this is non-zero, and this is on the, so this isomorphic to this Vi modulo Vi minus 1 localized at Pi. So therefore this localized at Pi is non-zero. Therefore, so that definitely implies the numerator Vi localized at Pi, this is definitely non-zero, because if numerator is 0, this module will be 0. But then if so, therefore this Vi localized at Pi, this is non-zero, and this is a submodule of V localized at Pi, because localization keep injections. So that means if Vi is a submodule of V, then further localization will also, it will be a submodule of the localization. So therefore I produce a submodule which is non-zero. In particular, Vpi is non-zero, and that shows that these prime ideals Pi's are in the support. So, and Pi's belong to the support of V. So, we have proved the other inclusion. So, we have proved this P1 to PR, P1 to Pn, this is a subset of the support. Now we only have to prove, so only need to prove minimal elements are same. Only to prove that minimal elements in the support are contained in the associated primes. So that means to prove if P is in the support of V is minimal element with respect to, of course, the natural equation, then we need to prove P belonging to associated primes of V. That means we want to find an element X so that P is annihilator of X for some X in V, for some. So there exists X in V such that P is the annihilator of X. That is what we want to prove. We want to prove some properties I will use one of the properties. So all right, so we started with the P in the support and P is a minimal element. Now when I localize, so V is here, then localize V at P. So there is a natural map here and we have the support of, this is the support. So if P is in the support of V, then it will, this is non-zero and therefore support of this module Vp as the AP module, definitely the image of P in the localization that should be there, and there won't be any more because all the prime ideals which are smaller, they cannot be in the support because we have chosen a minimal element, we have given a minimal element in the support. Therefore, the only possibility is this guy in the support and that is in the support. So, therefore, we have this, but all right. So, if I now, support is this, and on the other hand, also what about the associated primes of V localized at P, at A localized at P? This I want to check that this is non-empty. Once I check it is non-empty, let us first check it is non-empty. That is because if I look at these modules, since V localized at P, and if I further localize at a prime ideal Q A localized at P. So Q is the prime ideal which is contained in P, because in the ring A localized at P, the only prime ideals will come from A which are contained in P. The other prime ideals which are not contained in P, they will become unit ideals. So if I take any Q contained in P, Q prime ideal in A, and further localize this Vp at this I get, this is isomorphic to V localized at Q. This is an easy property of the localization. So this is this, therefore definitely the associated primes of this is non-empty because this is non-zero module, this is non-empty, and therefore the associated prime ideals. So that implies associated prime ideals of Vp as AP module, this is precisely PAP. There is no other way because we have proved that associated prime ideals are is a subset of the support. So the support has only one element, and this associated primes is a non-empty set, and it is contained in this. So there is no choice. So associated prime ideals of this must be this. And now use the localization. After localization, I have proved Vp, PAP is associated to Vp. So that will prove that P belongs to associated prime ideals of V. This is by the theorem we proved in the localization case. So that proves this theorem, and we will continue this discussion more in the next lecture, and there we will also discuss about what is called primary decomposition of a module over a Noetherian ring. Thank you very much.